Class begins EE 597 on Monday, July 25th, 2016.
Okay, so we've been talking about the network layer. And so far, really, we've covered a couple of topics. The first was the ETX as a metric. And just to refresh our memory, we talked about the packet reception rate as a function of distance. And we identified that in real systems, there are these regions where, to the left of a certain distance, you get perfect link quality. To the right of a certain distance, you get almost no packets being received. In between, maybe the mean behavior kind of decays down, but really what you observe is a lot of statistical fluctuation of the link qualities, and often it's kind of bimodal between being high PRR and low PRR. So this is sometimes called the transitional region. And we said that in typical networks, this region is quite large, which ends up meaning that 80 to 90% of your neighboring nodes might be quite flaky in terms of link quality. They may go up and down. It's really subject to intermittent link availability due to fading. Before we talked about ATX, we also talked about blacklisting, which also came out of looking at this type of a vision of what's happening at the link. So either you can choose for these links to identify who they are and blacklist them so they don't show up in your neighbor tables and end up potentially being a waste of your effort in trying to route. Or you can create a routing metric such as ETX, which will not favor nodes in this region and tend to favor the high PRR nodes. And we said to a first approximation, you can think of that as a first order approximation. Basically, if PRR is NIID, random variable, and if ACK packets always received, then you can approximate ETX as 1 over PRR. Okay, because it sort of becomes a geometric random variable whose success probability is PRR. So the expected time to the first success, which is the expected time to your first successful transmission being acknowledged, is roughly 1 over PRR. And then we said that in practice, it is measured as a moving average of instantaneous ETX, so I forget the exact expression we wrote down, but it's something like ETX for the n plus 1th time step is some alpha of the ETX at n plus 1 minus alpha of the ATX instantaneous. Okay, and the instantaneous ATX you measure typically by actually sending packets and seeing counting. Like when I send the last packet, how many times did I have to transmit before I got the ACK back? And this alpha is just a smoothing parameter, and you typically choose it empirically. And we said it's about 0.8, 0.9 is what ends up working out in many systems. But it's a parameter that if it's very large, you're choosing your previous value, so it's sort of changing the ATX estimates very slowly. On the other hand, if it's very small, you become very sensitive to rapid variations of the instantaneous ATX. And so in either case, it's sort of a measure of how good the link is, right? And so the basic idea of using ETX as a metric is, for example, if I have a choice, maybe between a couple of options, so I have a set of nodes that I want to route data from A to E. If I use min hop count routing, okay, may prefer longer hops. So what I mean by that is it may prefer, because you're trying to minimize the total hop count, maybe you'll create a network where your data goes to node C, which forwards it to E. But the problem with these longer hop count nodes is that they're more likely to fall into this region. And so maybe when you first added them to your routing table, they look good, but maybe when you're actually sending the packet, they happen to have undergone, a fading instance where the quality is really bad, so you send the packet and it actually doesn't receive, and you end up having to retransmit a lot. Whereas if you focus on kind of mini TX routing, balances both hop distance and number of hops. So it may not necessarily go, every single hop. It might turn out that the right thing to do for this particular network might be go from A to B, and maybe the link from B to D, despite being, maybe in this illustration it's not a good example, but let's just say we have another set of nodes in here. So maybe if you just went every shortest possible hop, it might be too many hops, but sort of ETX might give you something that's here. Right, so here, let me add some more nodes. So if you just went to pick the shortest possible hops, you might pick this particular route. But if you look at this particular route, it might take like 1, 2, 3, 4, 5, 6, 7 different hops to actually get to the destination. But maybe you could just have made it in 1, 2, 3, 4 hops, and they're all possibly also good. So ETX tries to find a path that each link is as good as possible, but also the total number of such hops is not too many, so as to minimize the total ETX count. Right? And we said that the ETX metric favors multiple objectives. So it favors reliability, because you're picking good quality links. It favors energy, because you're not doing so many transmissions. It favors latency, because each hop doesn't have to repeat on average many times, so that reduces the time it would take to move your packets. It also simultaneously will improve throughput, because it reduces the total number of transmissions at each node, which means it reduces the total interference within the network. And the less interference there is within the network, the higher the overall bandwidth or capacity of the network will be. So it's sort of a nice metric that simultaneously addresses multiple objectives. So that's one reason why in practice it's become very popular. So we said that mini TX routing can be implemented with standard Dijkstra or Bellman-Ford algorithm, which, as you know from even 450 or 551, if you've taken it, are basically link state or distance vector based protocols. Right? So you can take existing protocols like RIP or OSPF, and you just change the metric from just hop count to ETX. And so long as for every link, each node is able to maintain this quantity and has that available to it when it's making the routing decisions, you can create end-to-end routes in a static multi-hop wireless network that gives you many ETX routing. We then talked about last week something called any path routing. And we found that it can reduce total end-to-end ATX even further. And the basic idea of any path routing is that it uses the diversity of receivers, right? Or another way to say it is that it sort of exploits the broadcast advantage in wireless. And we discussed last time the basic idea that if a certain node wants to communicate to some final destination, while many TX would have chosen one of the possible receivers, with any path routing, you might choose a prioritized forwarding set. And the basic idea is that when you're transmitting, you say that it's okay for any one of them to forward with the priority that maybe you want node number 1 first, then node number 2, and so on. And if node number 1 gets that packet, it's going to forward it. If node number 2 gets the packet, but 1 does not, then 2 can forward. And if any of the above nodes have not received the packet, then this node can forward. And by allowing this diversity of potential forwarders, you reduce having to retransmit the packet from I to the first node multiple times just to make sure that it gets it, because somebody will have gotten it. It does require you to solve a coordination problem. It requires solving a coordination problem, which is that, for example, node number 2 and 1, when they both receive the packet, we want to make sure that they both don't forward, but rather that only one does, and typically implemented with a timer. Plus ACK. So you have a timer which says that if you're second in the priority order, you don't send right away, you wait to see if somebody higher than you has received it, and the way you can tell that is that they will ACK back the packet, and you listen to the ACK and then suppress your transmission. Alternatively, you could also listen to the forwarding of that higher priority neighbor and use that to stop your forwarding. In fact, a third way would be so all of these things can happen. If you're node number 2 and node number 1 got the packet, when it receives the packet, it's going to ACK back. It's going to forward the data packet. And in fact, the final destination will also ACK back. So depending on how you set the timers, you can even have to wait to hear this ACK, which, because it's by definition supposedly in range of this receiver in order to be able to forward to it, it will hear that ACK for sure. Even if for whatever reason this node was out of your range, if you didn't hear this or hear this, you have another chance. You may have sort of multiple opportunities to hear that a higher priority node has forwarded and you don't need to forward. So this is something that is required, but in practice, this is how you would implement it. Worst case, you make a mistake in the coordination and you also send a packet. It's not the end of the world. It's just a little bit of an extra inefficiency in that particular instance. Hopefully it doesn't happen all the time. If it does happen, node D needs to know that it's receiving a duplicate copy of the same packet and simply drops it or ignores it, rather than also treat it as a routing packet. So at least your errors don't have to propagate throughout the network. In order to implement any path routing, we cannot use Dijkstra-Bellman-Ford as is. We actually have to modify it, and that's what we discussed last time, is that any path routing needs modifications of Dijkstra or Bellman-Ford, in fact, to work. And in class, we discussed the I forget what it was called, anypath first, open anypath first routing. Actually not open, shortest anypath first algorithm, which really generalizes Dijkstra. And it generalizes in the sense that if it turns out that your network is such that there is no benefit to having a forwarding set larger than 1 for any of the nodes, the answer it will return is the exact same answer that Dijkstra's would have returned. But if some of the nodes could benefit by having this anypath set to reduce the ETX further, it will return that. So it generalizes it. It gives you a better solution than you would get with shortest ETX routing. So this is a kind of routing protocol that in some sense only makes sense for wireless networks. This really takes us beyond what one might have encountered in a pure wired setting. The one caveat, though, is that anypath routing sort of assumes a high density network, or at least, let's say, a non-sparse network. Right? Because if every node only really has one possible node that could help forward the data, there isn't enough diversity to be able to exploit the broadcast advantage. So it really requires there to be diversity of receivers for each node to move the packet along. So it may not be suitable for every type of wireless network. And in particular, also assumes omnidirectional radios. Right? I mentioned that some of the static multi-hop networks that have been deployed, such as the mesh network deployed by this company in Boston called NetBlazer, actually uses directional antennas. So they've actually set up their nodes so that each, even you may have 3 different nodes that could potentially route you to a final destination, but the way the communication is set up, if you're going to talk to this neighbor, you're going to use a directional antenna which will not simultaneously be receivable at the other nodes. Right, so if you have a directional wireless network, it's almost like a wired network. It's sort of, you talk to this receiver one at a time. So if that's the case, the broadcast advantage is lost. You're not going to get the diversity benefit. So, right, so if you have a more broad, more omnidirectional pattern, then you might be able to exploit the diversity benefits of anypath routing.
Those 2 nodes are not able to, like, they are not in touch, like, if whenever it sends the acknowledgement back and it listens to that acknowledgement, getting to know, what if those 2 are not in?
Yeah, so for example, let's just take nodes 1, 2, 3, and let's focus on 1 and 3. Let's say for whatever reason there is, I don't know, a big wall here between 1 and 3, right?
Okay. Yeah, one of them is on this side and they're targeting on something onto the.
I mean, does this example cover what you're concerned with?
Number 2 node is onto this side.
Yeah.
And this destination node is on the front side. Like,
Okay, so and then?
So, like, the 1 and 2 won't be able to hear to each other.
So I'm just creating a similar scenario where 1 and 3 won't be able to hear each other, right? Okay. So let's just take a look at this example and see what would happen, right? First of all, it must be the case that 3 is worth including in the anypath set. And the only reason for that would be it at least has good quality, relatively good quality links to both the source and the destination, even if it doesn't have a good quality link to the other, potential relayers. So I said that in order to use the prioritized list, there has to be some coordination that ideally 3 needs to know if 1 transmitted it or not, right? So there are 3 different places in which 3 can find out that 1 has transmitted. The first place it can find out is this ACK, which can only get through if 1 and 3 had a good link, so it won't. The second place it could find out is when one forwards, which is only possible if there was a good link between 1 and 3, which it won't. But the third place in which it can find out is when the destination acts back the forwarded message, and presumably this link is good. Because if even this link is bad, probably it wasn't a good idea to include 3 in your set to begin with. So this is sort of the scenario where the ACK coming from the final node is needed. Yeah, generally that's the most robust thing. So you want to make sure you're delaying your forwarding for nodes lower down the priority list long enough for the forwarded packet to have been ACKed back by the intended destination. So, in fact, this also raises an issue which isn't covered in the algorithm that we talked about, which is that it could introduces some additional latency. Because if you're wanting to exploit this diversity of neighbors, the more neighbors there are, the more diversity there will be. But if it turns out that you're very frequently going down lower and lower into the list, you have to end up waiting that long before you can complete this forwarding process. On the other hand, let's just say let's not necessarily. On the other hand, the reason it's introduced that latency is that one didn't receive the packet. The alternative would have been for the source to retransmit that packet anyway. So it's not like you were getting away with something that you wouldn't have incurred in any case from the... So the further down you go on the list, each time that you go down, it's because somebody else didn't get the packet, right? And so at a minimum, you could have had the source retransmit that packet. That would also have introduced some latency. So it is possible that it'll add some additional latency. In practice, people haven't found this to be a significant enough concern necessarily. Although I have to say that anypath routing, as far as I'm aware, has only been implemented and tested in sort of lab prototypes and not in real systems that are deployed. So this is still something that's making its way into real systems out there. But certainly, the measurements on testbed suggest you do get the improvements we're talking about even in real implementations. So I want to talk about a couple of other approaches to routing. And the first of these sometimes goes by the name of cooperative routing or barrage relay, depending on which paper you read. And there were sort of different people who came up with routing protocols based on these ideas and gave them different names. So for example, there's a protocol out there that goes by the name of barrage relay networking. And in the sensor networks community, there's a protocol called Glossy. And these papers have a very simple idea at the core of it. There's some additional details. For example, this is implemented in the products of a company called Trellisware, which I mentioned, I think, in our discussion about multi-hop networks. These have been deployed in the field in even mobile ad hoc networks, and Glossy is something that's been sort of used in wireless sensor networks. So the basic idea of this class of protocols is so the first is that it requires all of the nodes to have synchronized clocks. It's a scheduled mechanism that requires everybody to know exactly when a slot starts. And at any time, the entire network may be focused on helping just one packet be broadcasted, and really throughout the network. And the phrase broadcast shows up here. Barrage relay and glossy both are trying to get the packet from the source node to either everybody in the network or a lot of nodes in the network. That's sort of their use case. And examples of wireless networks where you might want to do this is maybe, for example, it's a group of firefighters, which sadly happens to be very timely in our region. But if you have a group of firefighters that are out there, you don't have a cellular connectivity out in the mountains. It's not like they can, call each other on their cell phones. You're trying to establish a network where they can coordinate their operations. Who is where are they going? And this really often requires for them all to be able to hear where everybody is, right, or what everybody's doing. And so it's really almost a network that is inherently a multicast or a broadcast network. So when one person talks into their walkie-talkie, you want that information to be broadcast to every person in that unit. And so in that case, whatever that message is that you just spoke, whatever the packets are, each one of them needs to be broadcast to everybody. And in these protocols, the idea is that we're not just trying to find a route for that data to take through the network to get from source to destination. First of all, there's not a single destination, it's everybody. Second, it's not just a particular set of nodes that are going to help. Everybody's going to help that packet get there. Okay? And so because it's a broadcast system, the basic idea is at each scheduled slot, all nodes with the packet will transmit that packet. And the analogy that I like to give to help understand this class of protocols is, I don't know how many of you have seen these soccer games in the World Cup, or very, very large soccer stadiums, and you sometimes hear a chant that the crowd is making. And if everybody was speaking completely out of time with each other, completely asynchronous, all you would get is noise. Right? In fact, that's what you typically get in a crowd. You get a lot of noise. But if everyone was able to synchronize what they were saying together, what you end up with is a really loud signal. You're basically getting a lot of constructive combination of the signals being synchronized with each other, and you're overall increasing the volume of that signal. So that's the idea, is that if we could somehow synchronize every transmitter in the network to the same clock, and these are the times at which they will forward the packet, and they know the start of that time slot, and they line up their transmission identically. Moreover, it's a broadcast packet, so there's nothing different between two nodes forwarding that packet. So it's not that they add a different MAC header to the same packet. They have literally the same frame, and not only at the network layer, but down to the link layer, and even down to the physical layer, the signals are identical. Okay? And so they're really, the key idea here is that synchronized transmission of identical signals from multiple sources increases the SNR, right? I'll say the effective SNR, sort of improving range and reliability. So it becomes more likely that any node that's hearing this loud signal coming from every node in the network synchronized with each other, it increases the possibility that you decode it correctly, and it also potentially increases the range over which you can decode it correctly because you're able to hear it farther. So that's really the basic idea. In practice, what can be concerning is how well do they have to be synchronized, right? So that could be, one question. Close or accurate, really is the word we're looking for. A related question might be, can the signals combine destructively. So what is the issue? So one is, let's say we had two sources and we had a destination, and they're sending their signals. Let's just indicate them by a sinusoid. And if the two sinusoids are lined up together, you would get a louder sinusoid at the receiver, right? But on the other hand, if their synchronization was off by 180 degrees on this signal, so half a wavelength, that would be bad, clearly, because then the two signals would leave and they'd perfectly cancel each other out. So at the receiver, you would get nothing. Right? So the synchronization clearly has to be the order of, if you're trying to do it at the physical layer, intuitively on the order of the wavelength of the signal. Or a different way of putting it is really the time has to be within, or like the delta t has to be less than like 1 over the carrier frequency of the signal. Right? So the carrier frequencies of these signals being, let's just take a standard ISM band radio. We're talking about 2.4 gigahertz. That's let's just say 2 times 10 to the 9 in units of inverse seconds, which if you invert it is really, talking about something like 10 to the minus 9 seconds. Okay, half, but roughly. So which is like nanosecond accuracy. Okay. That can be pretty hard actually to achieve. So certainly getting things down at the physical layer to that level of accuracy is going to be hard to do. Some of the schemes that are out there in practice, in general, it's going to be hard to do that. On the other hand, at the physical layer, in fact, we already deal with larger delay spreads. Okay. What is delay spread? If you remember from our earlier discussion about the physical layer, your packet from the transmitter to the receiver is typically not just a direct signal, but a bunch of reflected signals from different components, right? So each of these components traverse slightly different distances. And when you took all of those into account, what you got at the receiver was, the line of sight signal showed up at a particular time, but maybe a bunch of other signals show up at later times. And that time span over which they showed up, that is called the delay spread. Okay? And we have mechanisms including, coding mechanisms, CDMA techniques. We have rake receivers in CDMA. We have equalization schemes and so on that are there to deal with signals being received with slightly different phase shifts. And so even in this environment, even if they're not, in fact, nanosecond level synchronized, there are physical layer mechanisms which can mitigate a lot of that delay spread that's going to end up happening. So you can think of the slight asynchrony as being equivalent to delay spread. And so techniques that are deployed in wireless systems to deal with delay spread, and the equivalent of that in the frequency, it's called frequency selective fading, can also be applied to receivers for cooperative systems. So for example, the radios that Trellisware sells do two things. First thing, what they do is that, in fact, this relates a little bit to the second issue, which is that they may combine destructively, not only if they're starting from the same location because of time sync issues, but because maybe the two transmitters that are talking to the receiver are coming from different locations, and the distances between the two transmitters and the receiver may also be off in such a way that they might combine destructively. So one way to deal with this issue that's used in the Trellisware radios, for example, is called phase dithering, which is that transmitters may intentionally introduce a random phase shift in the signal. And you can show mathematically that, if I have two signals A and B that are both sinusoids, and I'm adding them up, of course the final result, whether it's constructively interfering or destructively interfering, will depend on the phase. So if two senders happen to be in such a location that they would be out of phase, if they're perfectly synchronized in such a way that it shows up 180 degrees out of sync, you're going to get nothing, right? Or you're going to get a destructive interference. But if what you did was you kind of randomized the two sources so that their phase is not exactly lined up, but in fact is adds a sort of random phase shift to it, then what you end up receiving is a random addition of two random sinusoids whose phases are, in the worst case, they might be completely out of sync, but they may also be exactly in sync, or they may be somewhere in between. That in this case, when you add the sort of random phase shift, you still get a signal that on average is louder, okay, than either in isolation. In other words, if I just heard A, if I just heard B, without the other being on, right, what I will receive if I do a phase-dithered combination of two sinusoids will actually be higher. And one way to convince yourself of this is to do a simple Matlab simulation. You take two sinusoids and you add them up and you look at the amplitude of the resulting sinusoid. If the two sinusoids are perfectly in sync, of course, you'll get a much larger signal. If they're perfectly out of sync, you'll get nothing. But now if you make those two, you run a for loop, each time you put a random phase shift to the two sinusoids and you add up, and now you take the average signal strength you heard after doing this random phase dithering, what you'll find is that the average signal is actually going to be louder than if I just sent one of them. Okay, I forget the exact number, but it's something like square root of 2 times the amplitude of either signal. It's not 2, which would have been ideal if they were perfectly synchronized, but sometimes it's hard to perfectly synchronize because you don't even know where the transmitter might be. They may be mobile and so on, right? And so in these systems, they are leveraging two sets of issues. One is use phase dithering to prevent any worst case scenario from persisting forever. Like if these two nodes were always stuck in the worst spot, you actually are making things worse. So phase dithering handles that by adding randomization. And on the other hand, you use techniques for dealing with delay spread to handle other variations in the phase synchronization. And the system in wireless sensor networks that's deployed, that's called Glossy, surprisingly does neither of these. It's much simpler than the system that's implemented by Trellisware. It just tries to synchronize their packets to within a symbol duration. On the sensor networks that are deployed, the symbol durations are on the order of milliseconds. So if you get things down to, not symbol, the packet durations are on the order of milliseconds. Symbols are on the order of tens of microseconds, which you can synchronize to. And what they show is that if you just synchronize down to symbol level, it's pretty good. That for some of these radios, the synchronization that is possible to achieve is enough to overall improve the signal quality so that the communication is very robust. So I'm not going into a lot more details here because looking at the actual stack, depending on how you're implementing it, there's a lot of details at the physical layer and at the coding and decoding and so on. But conceptually, these are the key pieces, is you must have some level of synchronization, right? And so typically only to symbol level, not to lambda level, right? Or 1 over frequency level, I guess is what I wanted to say. Okay, because achieving something that's 1 over carrier frequency level requires nanosecond synchronization. This is actually possible too. So nanosecond level accuracy is possible with GPS. Okay, let's just say if not to. So if you can achieve it, great, right? There's nothing like it. But in practice, in fact, if you just get it to within symbol level, it turns out to still be substantially better than if you were not exploiting the cooperative benefit. And the second is can improve performance by A, phase dithering, and B, phi/link layer approaches to handle, let's say, delay spreads. The point being that you already are suffering a certain amount of delay spread in your wireless channel anyway. And so now on top of that, there's some delay spread introduced by the fact that your sources are at different locations. And so if you have a system that's robust to those types of fluctuations, your overall reception here will also be kind of robust. And the practical implementations, both trellis ware radios and glossy have been shown to be very robust and highly reliable. And when I say highly reliable, I mean, for example, that if you use glossy in a multi-hop wireless network, you get close to 100% of your packets that are sent by any node in the network. And the disadvantage one might think of these schemes is that at any given time, the entire network is focused on sending just one packet, which means that there isn't a lot of reuse of like different links communicating different packets at the same time in the network, which could improve throughput. But that reduction in throughput is more than compensated for by the fact that every packet is reliably received by everyone. Plus, if your application already requires that you try to reach a lot of nodes, that's in any case what you might do. You might try to flood a packet, and this gives you the most efficient, most robust, most reliable way of flooding. So if people have relatively small-scale wireless network, let's say on the order of 30 to 100 nodes, and they want reliably for every packet to be received by every node in the network, this type of an approach cannot be beaten by a pure routing approach. So you're not better off trying to create routing tables and identifying the shortest ETX route or the shortest anypath route, which would be for a pair of nodes the best thing to do. But if you really care for multiple nodes in that network to reach reliably that message, you're better off just basically blasting the entire network with this message. So it will take a certain number of time steps. What we've shown in theory is that the total number of transmissions can show in theory that the total time needed is much less for cooperative broadcast. So I'm going to call this class of routing protocols cooperative broadcast routing. So the idea is the following. So if I were trying to get some message from a given node to particular network that happens to be deployed at some scale, if I have a very simple idealized model for propagation, you might expect that at each time I would cover basically a larger and larger range, right? So first everybody who was within this circle would hear me, then maybe everybody in this circle would hear, then everybody in this circle would hear, and so on, because you're sort of sending the packet, whoever receives it forwards it, whoever receives it forwards it. So in a very simple network, you might expect that the time to broadcast should take or you might think, sorry, let's put it this way, should be kind of, so traditionally at least, okay, would be proportional to what we call the hop diameter or hop radius. So what's the hop radius of the network? If I take the distance to the node that's farthest away, and let me call that distance d, and if I say that roughly, on average, each transmission typically captures all the nodes within some radius r. Now we've learned that this is not a perfect model for how wireless propagates. In fact, this range itself has some variation. But for now, just for conceptual understanding, let's assume an ideal radio that everybody within this radius r hears you, and everybody outside doesn't. So in this particular case, d over r is the hop radius. Right? Why? Because that's how many hops you have to go to reach everybody. But for cooperative broadcast, what happens is the range R increases at each iteration. And not only that, it increases geometrically. What do I mean by that? So in the first round, I capture a bunch of nodes and they transmit. Okay. Now, the first node, when it was transmitting by itself, had a certain range. But after that first round of transmission, it's joined by a bunch of other nodes who have all received the packet after round 1. Now, when they all transmit together, it's not going to just propagate to this distance, but because they're cooperative, it's going to go a little bit further beyond. Right? That's the whole benefit of trying to do cooperative synchronized transmission, is you're improving the SNR. And if I improve my SNR, effectively I'm improving my transmit power, if you will, if you want to think of it that way. So if I can boost up my transmit power, it's going to reach farther. Right? And so because it'll go farther, now I will get more nodes in that second round. Now all of the nodes that are in that second round are synchronized, and they're going to transmit at an even larger transmit power, because the number of nodes that I'm having within that radius is quadratic in the radius, right? If everything was uniform. And so now I have, maybe this was 1, maybe this is instead of 2, maybe even, went a little bit higher than 2, let's say 3. But now the number of nodes within that is something like 9 times as many nodes as there were in the previous round, okay? And that's going to boost the signal even farther. So the next time around, it won't just go a little radius up. It won't even just go as far as this one went, but even farther. And so what it looks like actually with cooperative broadcast, if you want to kind of imagine this, is that each time the range is getting larger and larger. Okay? And so this was like R1, R2, R3, R4, and basically Rn plus 1 is bigger than Rn as more nodes transmitted each round. Okay? And what you can show is that the size of these radii and the number of nodes that are involved in it actually the radius in particular, grows geometrically fast. And so that what it takes you to broadcast in let's say, theoretical, mathematical way of looking at this problem is that with broadcast, with cooperative broadcast, so traditional broadcast, the time was proportional to d over r. What you can show theoretically is that the time in this case is proportional to log of d over r. It sort of grows logarithmically with the hop radius, and so it's much faster, sort of exponentially faster. What it means is that in traditional ETX routing, it might have taken me 8 or 10 hops to reach that final node. With cooperative broadcast, it may only take me 3. Right? And so even though I'm involving all the nodes in my network and a lot more communications are happening, but because they're all synchronized, they're all sending the same packet, there's less interference, and because of the synchronization, the overall time taken to get the information is actually faster. And that turns out to be a very surprising benefit of cooperative broadcast, is that it's also faster. So it's reliable, can reach nodes that are further out, and on a related node, it's faster. So for applications where you really want to broadcast or multicast the data to a lot of nodes, and the network's relatively, I would say relatively localized and relatively dense, you might use cooperative broadcast as the mechanism. So I want to spend just a few minutes maybe identifying the papers that I'm talking about, and we will put them up for you to look at, partly because they're not very widely known yet and are still very much in the research community in case of glossy, but in the case of Trellisware, it's very interesting. The company was sort of founded, and the engineers that worked on it were not even aware of a lot of the literature on ad hoc routing, so they just decided to build their own radios for this particular class of applications which involve broadcasting. And the way they went about it had nothing to do with ad hoc routing, didn't have anything to do with distance vector or Bellman-Ford or measuring metrics. They just completely set all of that aside. So in cooperative broadcast, you don't need to have link metrics because it's not doing metric-based routing at all. So it's a completely different way of thinking about how do you construct your network and how do you propagate information on it. So let's look at these two papers that I mentioned, and we'll have links to them up as well. So this is one paper about barrage relay from the folks at Trellisware, and you can see Professor Chugh here at USC is in fact one of the co-authors of the paper. He is a co-founder of Trellisware. So, I mean, they do have clearly an academic connection, but not. So, let me show you any images from here. So here's like their description of what barrage relay network broadcast looks like. So you have the first broadcast reaches a set of nodes. All of those nodes that are labeled 1 will cooperatively transmit, and that might reach the set of nodes that are labeled 2 here, and then all of the nodes that are labeled 2 will transmit, and that will reach all the nodes that are labeled 3 here, right? In the example here, they're also talking about TDMA frames. The idea is that each slot might be dedicated to broadcasting a particular packet. So maybe over the same network, you're sending 3 different packets, A, B, C. Then what they would do is that at time slot 1, they would broadcast packet 1, which in the first time step would get to all of these nodes labeled 1. At the next time step, you'll broadcast packet B, which starts again from the source, gets broadcast to all of these nodes. Maybe at time step C, you broadcast it to these nodes. Then again on, and it doesn't have to be the same source node, by the way. The source nodes might be different for each of the packets. So maybe that this sender is sending all of the A packets, this sender over here might be sending all of the B packets, and so on. But so long as you have a globally synchronized clock, everybody knows when they're supposed to transmit which flows packets. They don't interfere across different packets, and at any given time, the entire network focuses on one packet at a time. So that's sort of the idea there. This particular paper actually does not get very much into the phase dithering, but I think there's a different paper by Professor Chugh that does talk about it. And that was an earlier paper going back to 2006 where they described using phase dithering for cooperative communication. So somewhere in here, it's sort of showing you that the signals coming from each of the radios are being combined by a mixer which introduces a certain phase shift. And this phase shift, if it's chosen sort of randomly, they show you what the benefits are. So for example, in this figure, it shows the signal to interference ratio for a given EB over N naught as you introduce different levels of phase dither, like how many different phase levels you might choose to randomize over, and shows basically that if you could do more phase dithering, you're able to get higher and higher performance overall. I'm not entirely sure what the comparison is against, but I think the peak on top is the curve for the case when they're perfectly synchronized, which if you could achieve, that's what you would want to do. But if you don't know where the transmitters are, you're worried that they might be potentially off phase from each other. So instead of correcting for that particular phase, if you just added random phase, it also improves performance substantially. That's sort of what those figures are showing. This is showing the performance with phase dithering as opposed to idealized cooperative, which would be this one. So the performance would be much better if you had ideal cooperation, in which everything is perfectly synchronized. But if you could get some level of phase dithering, they show that you can also get benefits with respect to that. Here's an example that compares dithering with not dithering the packets. So this is probably a more useful comparison. And again, it's showing for a particular type of modulation scheme, the bit error rate, when you have two users cooperating. If they don't dither, then there's a possibility that they may be stuck at a particular phase that is not going to result in constructive interference. And so in these two curves, they're showing how if you did dithering of the packets, you're able to get better performance. And on top of dithering, adding that phase dither, they also add coding. And part of the reason you're able to improve the performance is that you may lose certain bits in a packet or even packets in a set of packets, but there's coding to kind of recover from those type of failures. So dithering combined with error control coding is what their radios use. And this is sort of a paper that gets into some of those details. The other paper I mentioned in Sensor Networks is called Glossy. And here is the paper from 2011 where this is described. So the barrage relay networking paper, I think, is about 2010. This is 2011, so they came fairly close to each other. The anypath routing paper we talked about is probably 2009, 2010. So that's roughly when a lot of these ideas showed up. They're not that old. One reason we don't see them in a traditional networking course, for example, and why they're not really. Let me try this page. So the idea here with the cooperative broadcast scheme, of course, it's a type of flooding. And even just from their description, they talk about exploiting constructive interference for fast network flooding and time synchronization. They showed 99.99% reliability for this protocol. And there are figures here where they can compare it with other schemes. They do show some figures in this paper that talk about what is the synchronization that you need for this particular radio that they worked with in order to get the performance to be high. And you can see kind of the x-axis here is the synchronization between two transmitters. The y-axis is what percentage of time you were able to decode the packet. And it does show that in their particular scheme, which doesn't use phase dithering or error control coding, so it's a much simpler implementation of cooperative broadcast, that if you kept the synchronization between the two nodes to be within half a microsecond of each other, then you get good performance, but otherwise it can be pretty bad. Okay, so that's sort of their finding empirically for that particular radio. So half a microsecond is what they needed the synchronization accuracy for their network to be. So it's a lot of actual implementation details. We'll put up this paper as well if you're interested in learning more about how Glossy is done. So here is again their experimental evaluation, not just with two nodes, but with a larger number of nodes, that you're getting very high reliability for low synchronization values close to half a microsecond or less. And this reliability, actually, once you have about 4 concurrent transmitters, you're getting above 99% reliability. So that's the key is to get it to be above about 4 or 5 nodes nearby to be able to give that very high reliability. The synchronization error they're able to achieve, so what they do is while they're flooding the packets themselves contain timing information. So the very act of doing this cooperative broadcast is also helping them synchronize the network. And so each node embeds into the packet that it transmits what the local or the source node embeds the local timestamp that gets disseminated to everyone. And part of their protocol is to make every node in the network synchronized with the broadcaster. And that allows them to also maintain very low synchronization error, so it sort of feeds off of itself. An interesting side note about Glossy is that earlier this year, there was a competition they held at a conference called EWSN, and it was called the Dependability Competition. Let me kind of describe it to you here. So this is from their original call for competitors, where it was a competition. So you had one of these wireless devices would be sensing a light, and it would have to measure its brightness and communicate to the sync node if the light gets turned off or on, right? So that's the message that needs to be broadcast throughout the network. So the blue nodes are the nodes that your team would be allowed to put in the competition floor. And you could implement any routing protocol you wanted to move the data from the source to the sink, right? What they would do is they would place a bunch of these red nodes throughout the arena, and they would turn them on randomly to cause interference to your network. So you're trying to move data, but there's another network which is trying to jam your communications. And so the goal of the competition was basically you come up with whatever protocol mechanism you want, you design and implement it and deploy it, and then they would compare the performance in terms of reliability, latency, energy consumption, and the team that has the highest metrics would be the winner of the competition. So this is the competition that they announced. This is from 2016, this year, February. In the end, they actually published the results that they had. So as it happens, USC had a team from my group, Pedro Gomez, who's a PhD student, and Pradeep Ghosh, who's a PhD student here, along with a collaborator from France. We came in fourth in this competition, but it turned out that the teams that got the first place, the second place, and the third place all used Glossy. So that was sort of an interesting observation about the quality of performance. So our team number, just for my own benefit, was team number 8. And so you can see the reliability numbers of all the teams here. The top 4 teams in team number 8 was ours. All got reliability in the 90%, and the other teams had reliability down in the the 70s, the 60s, and the 50s. Of these top 4 teams, the first 3 used Glossy and got above 90%. The top one got 100%. Our team got 99. We didn't use Glossy. We had our own way of using multiple frequency channels to try and avoid the jamming. But it was using, other than that, fairly straightforward flooding. So it's flooding, but with multiple channels. So it turns out that Glossy was the most robust of all of the existing routing protocols. So whatever else was being used by these protocols, my gut feeling is maybe it was something like ad hoc routing, shortest path routing, things like that. They tended to do much worse in the presence of external interference compared to Glossy. So this is a good systematic way to see the benefits of Glossy in a realistic environment. We did clearly lose out because of our energy usage. We were, it turns out, dramatically higher in energy usage than any team. So otherwise we could have maybe placed second with that. Latency was another benefit of Glossy. As it turns out, the top team was able to bring the overall time on average that it took for the data to reach the final destination down to 13 milliseconds. And it's conceivable, I don't know for sure what they did. It is possible they may have also exploited some additional diversity benefits or even directional antennas or something. So anyway, so this is kind of one evidence in favor of Glossy as a broadcast mechanism that's very robust and potentially also low latency, and so on. Okay, so that was a scheme that I wanted to mention. I want to talk now about another class of routing protocols that go by the name of back pressure scheduling and routing. And this is a class of routing mechanisms that are sort of queue aware scheduling or routing. And I'll try to clarify the difference between scheduling and routing a little bit. But roughly speaking, by scheduling, I mean that you've told each node when to send a packet, and that's already figured out. Like it's like you've imposed the routing when you describe the scheduling mechanism, whereas routing is more of a traditional internet way of looking at things, where you have layer 2 is taking care of the link access as a randomized access mechanism, and layer 3 is just doing getting the packet to the end destination. So you don't have a specific schedule at which nodes are being moved through the network, which is really more of a layer 2 concern in many systems. So back pressure needs a little bit of a long introduction, because in fact the ideas go back to papers from the early 90s. So there's a paper from about 1993 by researchers Thasioulis and Ephremidis. And Professor Ephremidis is a faculty member at the University of Maryland. Professor Thasioulis was in Greece for a while, but he's, I think, now a faculty member at Yale. And they wrote a paper about back pressure that was an algorithm that they proposed called the max weight algorithm. And they proved a very remarkable statement about this algorithm. They showed in their paper that this algorithm can stably schedule any arrival throughput vector or rate vector that can be scheduled by any other let's say in a stable manner. Okay. So I'm paraphrasing their mathematical result, but even understanding the statement will require us to understand a few words in here. So first of all, I talked about an arrival rate vector. I talked about stable, and I've talked about scheduled. So let's kind of define each of these terms. But once I define these terms, the power of their result nonetheless can be understood intuitively, is that this algorithm can do something that any other algorithm could possibly do. And so in that sense, it's sort of a universal algorithm. And the reason their result was really powerful is that what any other algorithm could possibly do is maximize throughput. So you have a certain data rate you're trying to push through the network. Any other algorithm, the best algorithm you could find to schedule a particular amount of traffic from each of the sources and destinations in a network, it's going to find ways to move them through the network so that packets are getting where they need to go, and you don't blow up or drop data from the network anywhere. Right? So long as there's any algorithm that can do that for a particular set of data rates in the network, their algorithm can. In other words, their algorithm is enough to optimally schedule every possible throughput vector that is possible to schedule. Right? And the reason why one has to be very careful with the wording here is that there may be throughput vectors that nobody can schedule. Like if you overload the network with too many packets, there's just too much congestion, there is no algorithm in the world that can move those packets through the network without losing some of them. Then they can't help you. But so long as there's some way to move packets through the network without losing them, right? And whatever that set of data rates is for different sources and destinations in the network. If there's any way to move them through the network without losing packets, if you will, or blowing up queues, their algorithm can do it. So it's sort of a universal way of moving packets through a network, such that if the amount of data in the network is within the stability region of the network, they will guarantee that it can be stably scheduled. Okay. So we have to understand a few concepts here. One is stability, one is scheduling, and the other is what is a throughput vector. So let me define each of those terms a little bit carefully. So imagine a network. So given, let's say, a wireless network. So you have a set of nodes, and you have a set of maybe sources and destinations. Just call them S1 and T1. Maybe this is a source 2 that wants to get its data to some other destination. Maybe there's a source here. It's trying to get its data to T3. Let's say for now that we have some logical topology that's been constructed over this wireless network. So say we have a set of source destination pairs. For now, we can imagine these are all just unicast flows, right? So each has a unicast in fact, the result generalizes even to multicast flows. You could have had multiple flows associated with each, or it could be many nodes trying to talk to the same destination and so on. But for now, let's just take this simple example. So the unicast flows, let's label them. Let's call it just F1 through Fn. Then an arrival rate vector is a collection of rates R1 to Rn, okay, a set of data rates, one for each flow that describes traffic at the source nodes. The arriving traffic. By arriving traffic, I mean this is what they're generating that they want to get to the destination. Okay, each node in the network will maintain a set of queues, one for each flow. So let's put them as a superscript maybe. Okay. So each node I maintains a set of queues, one for each flow. So it's got QI1 up to QIN. Now, in practice, you only have one queue in which you put all your packets. This could just be thought of as I take that queue and I say how many of them are for flow 1, how many of them are for flow 2. So even if it's not physically maintaining n separate queues, you can imagine it's sort of, you're classifying where those packets belong. And intuitively, if you could serve them out of order, you could only do better than if you have to serve them strictly in order, right? So in general, if I have an optimization problem and I put some constraints on how you can solve it, that's going to give you a worse solution than if I don't put those constraints. So by insisting that I only serve whichever packet is at the head of my queue, I could only do worse than if I could pick and choose which packet from the queue I can serve in the network. Just because in one case I'm putting a constraint that you must do it a certain way. In the other case I say you can do it that way if you like, but you can also choose whichever one you want. Whatever you need to do to optimize, you can do. So then by having less constraints, I couldn't do worse, right? So in this case, we're going to assume that nodes are able to serve packets from each flow separately if they need to, like they can just choose at any moment to serve packet from Q3 or a packet from Q5 and so on. Whichever flow they want to serve, they're allowed to do that. In the stability framework, we assume no max size for any queue, but want the queue occupancy to be bounded, right? i.e., if I have at some queue, and for a particular flow, if it was getting larger and larger over time, right, this must be avoided, right? This is what we call in networking an unstable queue, right? Actually, this is what we call in network theory an unstable queue. In practice, there's never such a thing, because in practice, all of your queues are finite size. They can never go to infinity, no matter what you do. So instability is like a theoretical concept that we do a lot of our mathematical analysis with, because it turns out to be easier to work with. In practice, by ensuring that your queues are stable, what you're really saying is that there's a maximum value above which they don't go. And so long as my real queue is that value, I'm okay because I won't lose my packets. Right? So I'll just put this as an aside. Stability is a theoretical concept. Right? In practice, all queues are finite. And stability implies low drop rate or probability. So ideally, if you have, in theory, I can guarantee for a protocol that it keeps things stable. In practice, it might mean that in my network, which has finite queues, I'm unlikely to lose packets, because I have a stable system that kind of keeps each queue below some level. And so long as my queue size was at least above that, I'll be okay. Right. So this is a subtle point I wanted to make. So in order to take this class, I think the requirement was 503 for sure, but I forget if there's any other prerequisite. So like you don't have to take 550, for example, right? But if you took 550, you would see there this idea of stability when you analyze an MM1 queue. So an MM1 queue is a single buffer to which packets arrive, and the packets arrive with an exponential inter-arrival time, and they start filling up the buffer. So this is equivalent to something called a Poisson process. And then the queue basically goes to some server, which sends the packets from the queue with also an exponential service time. So this is called an MM1 queue. It's like the simplest type of queuing system we can analyze mathematically. So you have a server, packets or customers arrive, and they arrive with a Poisson random process with a certain rate, which means that each time they arrive, the time to the next arrival is an exponential random variable. The server, each time it gets a customer or packet, takes a certain amount of time to process or send that packet. You can think of, the server might literally be a cashier when you walk up to the cashier in a grocery store. It takes a certain amount of time for them to deal with each customer. How long that time is for them to deal with each customer is also exponential in an MM1 queue. If you have packets, this might be different times because you're processing each packet based on the address, the destination address. You have to find where in the lookup table that packet tells you, the routing table tells you which interface to send it on, On that interface, it might take you a random amount of time to send them on because of medium access reasons. So each packet takes a random amount of time to be dealt with before you can serve the next packet in a router, right? So this is the service time, this is the arrival time. If they're both exponential, then we have a system called an MM1 queue. So if in 550, I don't think we do this in 503 at all, but if in 550, or do you in 503 see an MM1 queue? Some of you might have. Some, but not all, depending on who you took it with. What you can show is that for an MM1 queue, this is what happens. If I increase the arrival rate, by which I mean the time between arriving customers gets shorter and shorter and shorter, then the delay, or equivalently, because of Little's theorem, the number of packets in the queue, up to the service rate. So certainly, think about what's going to happen. If your arrival rate is higher than the service rate, if you're arriving faster than they can serve you on average, then you're going to build up the queue. So over here, it's going to be infinity. Okay? And in this space, you have an unstable system. In here is the stable region. And for an MM1 queue in particular, you can show that it sort of gets, it's sort of low up to a point, and as you get closer and closer to the service rate, it starts to blow up. Okay? The occupancy of that queue gets larger and larger and larger. We've seen this phenomena in stores even, for example, where you find that the rate at which customers are showing up is faster than the rate at which that cashier can handle them. Right? If they don't have enough cashiers, for example, or they happen to have a particularly slow cashier, you'll see that this queue is building and building and building and building. In theory, what that's going to do if your arrival rate is really higher is it's going to blow up. But the closer you get to that point, the larger it gets, and it sort of tends towards infinity. Okay? And so this is the notion of stability we're talking about here, which is that all of these queues at every node in the network, they have packets coming in, they have packets going out. You want to make sure that none of those queues blows up. Okay? And again, as I said, in practice, they would never go off to infinity. They could just reach a point where they start to overfill the available buffer space and you have to drop them. Okay? So when we talk about the transport layer and we talk about congestion loss, this is what we're talking about, is that packets fill up at a router and it has to throw them away. So you don't want that to happen. So if I give you a particular arrival rate, so I have a particular arrival rate for every flow in the network, right? That's equivalent to the arrival rate we're talking about here, except instead of just for one queue, we're talking about one flow, we're talking about for a number for every flow. So the x-axis is no longer just a one-dimensional axis, it's sort of an n-dimensional axis. Okay? And the network itself has a certain service rate it can offer. And it's not a single number, it's a multidimensional number. It's how much rate can I give to flow 1, how much can I give to flow 2, how much can I give to flow 3. We've seen this idea of a multidimensional service rate already in Aloha, for example, when we were analyzing in CSMA, right? So the network has an n-dimensional arrival rate and an n-dimensional service rate region. Okay. And so the question is, just like here, everything inside that region is stable, everything outside that region is unstable. Okay? So this service rate region, the set of arrival rates that can be serviced without letting any queue become unstable, right? Colloquially blow up, is called the stability region. Now there's a subtle difference between the stability region for the MM1 queue, and the stability region for a network. In an MM1 queue, you don't really have a lot of choice in what you're doing. You have a server, and that server service rate is a fixed value. There's no trade-off, there's nothing to do. In a network, you have a lot of design freedom. You can choose how to move the packets between different servers. You can choose how much of each flow the server chooses to serve. So it gets like 3 different flows. It says maybe I'm going to focus on serving packet 1 right now, flow 1 right now, then I'll switch to focusing on flow 3 later, and then maybe flow 2 at some other time. So basically, in a general network, it's more than just a single queue. It's many, many queues, and they are deciding who to send packets to, which flows to serve, right? So the network chooses which links to schedule, right? So in other words, if I have node I and node J, and it says, I schedule this link between node I and J, it means that I'm going to move packets from the queues of node I to the queues of node J. I get to choose that, right? Which will be subject to interference. We've talked about graph coloring in this class. It may be that I can't just turn on all my links all the time. I can only turn on these links when these links are not on. I can only turn on these links when these links are not on. So that's one thing the network gets to do. Second, also it gets to choose which flows to schedule on each link. Yeah, let's just leave it at that. So the network gets to choose these 2 things. A mechanism that chooses these 2 things, we're going to call it a scheduling policy, right? So a scheduling policy chooses the link activation and flow service decisions at each time. So this is what happens. So you end up with a black box, and inside it is the scheduling policy. It takes as an input a set of arrival rates, R1 to Rn. And depending on your policy, it might make it either stable and make sure that all of that data from every source is getting to the destination, none of the queues are blowing up. Or it could be a terrible policy, and even though it could have made them stable, it ends up making them unstable. Right? So you take some policy, let's call it pi, and it takes an arrival rate vector, 1 at each flow, and either it's able to service them in a stable fashion, it finds a way to move the packets around, get them to where they're needed, so long as these flows last, so that nothing blows up, or it does something bad and ends up blowing up the network. For example, a really dumb policy might be, I will only serve flow 1 all the time, and I won't offer any time to service flow 2. Then if any arrival rate vector shows up where flow 2 has a non-zero value, I'm not able to move those packets across. That causes, at the source, flow 2's packets to keep rising, and that blows up. Or I might choose to schedule one link more than I need to, and another link less than I need to in order to clear the packets from my network. And so the policy could be a bad policy and end up resulting in an instability, or it could be a good policy and make things work. And the claim is that for every, so let's call this vector lambda. Okay, so it's now a vector. For any lambda, if there exists a policy pi such that lambda can be serviced stably, okay, then we say that lambda belongs to a set, let's call that capital lambda, where This capital lambda is called the stability region. Okay. So notice that it doesn't tell you which policy we're talking about. It says if there's any policy at all that can guarantee stability, then this arrival vector is within the stability region of the network. So the stability region of the network is not specific to a policy. It's something that says, is there any way at all that I can do this? Okay. So theoretically, it's possible that for every arrival vector in this region, you need a different algorithm to ensure stability. That could happen, right? But what the CLS and Ephemeris proved was that, in fact, no, you don't need that. There's one algorithm that for every lambda in this region can guarantee stability. Does that make sense? So just one scheduling policy or algorithm called max weight can guarantee stability for all lambda in lambda. So that was really why the result is powerful, is that, this description is reasonable. It just says, is there some way that I can serve this rate? But what they're saying is they have an algorithm that can service every rate that any other algorithm could possibly make sure it's stable. Their algorithm will make sure it's stable. If no other algorithm can make sure it's stable, theirs can't either, because that probably means that you're overloading the network. Okay? So, to build a little bit of intuition, I really like, when we're thinking about networking problems, to think about something in the real world that you encounter on a daily basis that applies to the concepts that you're learning about. So for some reason, when I think about stability regions and servicing, I think of a very unusual bathtub. So the bathtub has a bunch of different taps, and it has a bunch of different, well, let's even take, that gets too complicated. Just the drain that it normally has, but it has a bunch of different taps. Okay, some of the taps pour out red liquid, some of them pour out blue liquid, some of them pour out green liquid. And what you have to do over time is to turn on the taps and turn off the taps. You're not allowed to turn on more than one tap at a time, right? And behind the taps is a reservoir at which somebody keeps pouring in these liquids at a certain rate, okay? And so what do you have to do? You have to turn on these taps and turn off these taps over time to make sure that none of those reservoirs that are showing up get backed up to the point where they just keep increasing nonstop. So you have to kind of make sure that you're servicing, if you will, in this case, all of those different flows, literally flows of liquids, by choosing taps to turn on and off. So turning on these taps and turning off the taps is like scheduling the links or the flows that the network can do. And ensuring stability is a matter of making sure that all of those are getting drained at a rate faster than they're coming in, right? Because if any of those taps is being turned on in frequency in such a way that it's such low frequency that the rate at which you're able to clear that fluid from the tub is slower than the rate at which it's arriving, then that particular tank is going to overflow. Right? So that's the type of problem we're dealing with here. And what they're saying is they have an algorithm to make sure that no matter what the arrival rate of those different liquids is, you can make sure that they're cleared out if it is possible to do so. It may turn out that somebody cheats and puts so much liquid in all of those that it doesn't matter which one you turned on and how you did it. There's no way for you to clear all of them out in time. So they may arrive too fast for you. But if that's not the case, there is an algorithm which can guarantee stability.
What's wrong in having just one queue and just serving the way it's coming?
So in this particular example, you might be able to, because you can pull all of them together. In practice, those queues might be located physically at different nodes in the network. And it may turn out also that you have to service some queues at a higher rate than others. And so by putting them into different queues, it allows you to focus more on certain flows than others. So we might see a little bit of that when we see the details of the max weight algorithm. So it does preferentially allocate the links to queues that are more backed up than others. But if you treated them all as the same queue, you might not be able to separate between those instances. So here's the max weight algorithm itself. Oh, our time is up, so maybe I'll have to wait, but I'll give a quick intuition. So the idea is for every link and every flow, we look at this quantity, and Wij star is the max overflows of Wij(f), and schedule so this max over f, we call that f star. Schedule the links and flows, let's call that f star, such that summation of Wij f star is maximized and interference are considered. So what I mean is you only schedule links that respect your interference constraints. So you're not allowed to turn on links if they're going to interfere with each other. So you turn on links in such a way that the total number of links that you turn on, if you looked at this Wij star value on those links, that's going to be as high as possible. So, and the way you come up with these weights is you look at the Q differential between node I and node J for each flow, and you take the maximum over all flows of that Q differential. So this is called a Q differential, or Q back pressure. Okay. And by maximizing this weight over all of the links that get scheduled at that time and repeat, so repeat the above at all times. Okay. It's a very simple algorithm. Really, this is all there is to the algorithm. And you just keep doing this. What they prove is that if there's any way to ensure that a set of rates can be stably scheduled, this simple algorithm can do it. And all it does is it tries to maximize this weight. This is the weight in max weight. Okay, so we will stop here and continue next time. And where I want to take this is to show that you can go from their theoretical result and actually develop a real routing policy that performs well in practice. And we have implemented such a policy for wireless sensor networks, and I'll talk about what the practical benefits are.
This concludes E597 on Monday, July 25th, 2016.